This is when we have a large amounts of packets and we can lose some data. So how can we, if it's not a TCP session, TCP is going to automatically recover from all losses of data. But we can't do TCP with streaming audio and streaming video and voice over IP traffic because it would cause too much overhead. So if we're experiencing this type of problems with it, we should increase our link capacity, go from a gigabit connection to a 10 gigabit connection, and use tagging of traffic to make sure that our fragile information, our voice over IP information, gets put to the head of the line. And if traffic does have to be dropped, maybe we can drop some lower priority traffic and not drop the higher priority traffic. Remembering that voice over IP doesn't need big buffers, big packets. It just needs a very small amount of guaranteed bandwidth and a small amount of guaranteed latency, so it doesn't mess up the voice conversation. So what we're going to do is classify and mark our data. We're going to take our Ethernet frames that contain voice over IP and mark the frame. We're going to take our IP packets that contain streaming audio and video, and we're going to mark that packet. Kind of similar in concept to when we marked our Ethernet frames to see what VLAN they were in, so we could tell where they could go later. Well, we're going to mark them with another type of mark that says this is high priority traffic, this is voice over IP traffic. And another tool is going to be congestion avoidance tools. We're going to, maybe we've got a gigabit of traffic in our production network and our WAN connection is only 200 megabits. If we don't do something to avoid trying to cram a gigabit of data over a 200 megabit line, which is only 1/5 of the capacity, we're going to need to be able to filter that so it doesn't overwhelm them. Because otherwise it's going to be a drop according to our carrier's rules and not our rules. So there are some tools for this, algorithms for this that will allow us to tune this up if we're having a lot of congestion. So here we see in the left-hand side the classification and marking. A bunch of packets are coming in, and we're classifying them as, high priority, medium priority, lower priority. And then when we get into the congestion avoidance and the routers, they're going to look at this traffic, and if it exceeds the amount of traffic, that our WAN circuit is capable of handling, it's going to selectively drop some packet, drop some information. It'll try to keep the voice over IP and the marketing manager's video teleconference stuff at the top of the line, and it'll drop the packets for a huge FTP download that someone's doing because it's the last business day of the month. And that's okay. TCP will eventually recover that data. It'll just take that file download a little longer to take place. And then at the congestion management end, we're going to queue up the most important data and schedule it and shape it. We'll talk a little bit more about shaping later to make sure that it doesn't exceed the capacity in our WAN connection that goes back to the other office. So what we're going to do is tag or classify packets or frames depending on whether it's layer 2 Ethernet frames, most likely, or layer 3 IP packets. And we're going to do this using the particular interfaces they flow in and out of, access control lists, and something called class maps. Now at layers 4, the transport layer up to the application layer, there's also another method using network-based application recognition, or NBAR. So let's look at how we could mark these things at layer 2 and layer 3. So when standard old wired Ethernet has a class of service, 3 bits in it, 3 bits of width that we can mark frames with. This will be carried by all the switches. Even if this access layer switch is not aware of this marking, he'll go ahead and carry the Ethernet frame unchanged. He's not going to do anything to it. If we're using Wi-Fi, Wi-Fi has got 3 bits for the Wi-Fi traffic identifier that we can use to signal. Now think a second, put on your binary hat. 3 bits. How many different things can I say with 3 bits? Well, 2 to the power 3 is 8. I can say 8 different priorities or 8 different markings with a 3-bit value. Multi-protocol label service is also got 3 bits. That's a layer 2, really kind of layer 2.5 type of thing, similar to the old frame relay where you could go to a service provider and he would put multi-protocol label service labels on your packets and frames to make sure they go to the right remote branch office on a private line. Okay, at layer 3 with packets, both IP version 4 and IP version 6 have this IP precedence field, which is 3 bits, so I can have 8 different signals, 8 different commands. And then the differentiated service code point has got 6 bits. So to the power of 6 is, let me say I only went to public school, but that's like 64 different commands or configurations that we'd use with 6 bits. So let's mark it layer 2. Look at that green frame at the top, a standard Ethernet frame. When we put our 802.1q tag on that Ethernet frame, and on any normal business environment, we're going to be using, in a small business, maybe 3 VLANs, students, faculty, administration. So we're going to put that 802.1q tag on it. Now, before, when we looked at this tag at the bottom, this VLAN ID blue at the bottom of the graphic, that was our 12 bits for our VLAN ID. So with 12 bits, that means we can have 2 to the power 12, about 4,096 different VLANs. There's a few that are reserved. We only get about a little over 4,000. But there was a priority, the purple. So we can use this for quality of service. With 3 bits, we can signal 8 different things, 8 different commands, or 8 different configuration things to be set. So that's how we can mark it layer 2 on the switch. So the value of 000, which is a binary value of 0, that's different. That's the default. If it's medium priority data, we're going to mark it with 001, which is the binary value for decimal 1. If it's high priority data, we're going to mark it with the 010, which is the digital value that's equivalent, the binary value that's equivalent to decimal 2. 3, we're going to mark it with 011 for call signaling. 4 is used for video teleconferencing. Our actual voice traffic, we're going to mark it very high. 101. Layer 6, or the values for 6 and 7, are currently reserved. So this way, when you set up a call, it'll have a medium level of priority. When you're doing video teleconferencing, it'll have a slightly higher level quality. But that all-important voice over IP traffic, because businesses run on people talking on phones, that will be at the top of the list. Now let's look at layer 3. In IP version 4, we've got this type of service field where we can support an 8-bit field. In IP version 6, it's called traffic class, same 8 bits. So we can use our quality of service classification to mark this, use 3 bits for IP precedence. And that was the old standard. The new standard extended it to 6 bits. And they're backward compatible with each other, kind of like RIP version 1 is backward compatible with RIP version 2. You can use them both, and they sort of merge with each other. And the values, the old values are consistent with the new 6-bit values. The 3 bits that the old one had is the same, where they will be consistent with each other. So this values is best effort default 0. Just no more routing. No quality of service. If the router gets full, its buffer memory gets full, he's going to drop the packets in a sort of a first in, first out order. With expedited forwarding or assured forwarding, then we can use this marking to make sure that the voice packets get put to the head of the line, or the video teleconferencing stuff gets put to the head of the line. So here's the formula for assured forwarding, and with these are the 3 most significant bits for the class. 4 is best, 1 is the worst, and then the 4th and 5th bits are used to designate in what order did these things get dropped, and 6 is currently set to 0 and not being used. So class selector bits, the 3 most bits, this is the backward compatibility thing, the green bits and the purple bits. The old method was use 3 bits, COS. The newer method is DSCP, uses 6 bits, but the 3 bits mean the same thing. They sort of overlap with each other. So they maintain compatibility with the older standards. Okay, do you remember when we talked about DHCP and which port ports should be trusted ports that would allow DHCP offers to come from a DHCP server, and other ports were untrusted ports that would not accept the DHCP transmission to prevent that idiot vice president of marketing from setting up a Linksys router because he wanted to go to the break room and use his laptop computer, and he didn't realize that that Linksys routers are DHCP servers, and it would have messed up the rest of the company. So this is a sort of a similar thing with quality of service. We can have trusted endpoints that can mark traffic, and we can have untrusted endpoints that are not allowed to mark traffic. So for example, in the classrooms, in the faculty offices, there's one wire that comes from an access layer switch to a Cisco phone, and then the Cisco phone has a second RJ45 that plugs into the computer that used to plug into the wall where the Cisco phone is now plugged into. The Cisco phone is trusted because he has to be able to initiate a telephone call, and we want to mark his frames and his packet as, you know, getting high priority. And of course, the access layer switch and distribution and core switches and the routers that are connecting me to the other locations all belong to this same club so that they can make the expedited access stuff work properly. PCs themselves, we're not going to trust them. They're going to be they're not going to be marked as secure. Okay, let's look at congestion avoidance. This is a problem that if I've got a gigabit or 10 gigabit based LAN at my location, and then I maybe only have maybe I got 10 gigabits at my data center, and I only have 1 gigabit connection to the WAN. Or I've got 1 gigabit to my employees and only have like a cable modem with 200, 300 megabits to connect it to another location. So congestion avoidance is a way of monitoring our network traffic and to try to avoid congestion, because what happens if I do have a burst of traffic on the last business day of the month and I have a whole gigabit of traffic trying to go to that outbound WAN interface back to the home office. So one example of an avoidance technique is weighted random early detection. It tries to manage the buffers and try to tell the TCP, because TCP has one of the mechanisms of TCP is for a server hitting a file to signal back to the client how many bytes he's willing to receive at one time, and he can throttle back, and that can help reduce congestion. So let's look at the difference here between shaping and policing. Traffic shaping is a thing that will smooth out the outbound traffic so that's consistent with the maximum bandwidth that we're able to send over a WAN circuit, for example, so that smooths it out. Policing is some people on the freeway are going slow, some people are going fast. The police are going to stop the people that go over the speed limit and get a ticket. They get chopped off. So policing doesn't shape it up. It just chops off all the traffic that exceeds the bandwidth, because we don't want to go into our service providers' WAN connection with this excess traffic and have it being dropped by their rules. We want to use our rules. Okay, some guidelines. Enable queuing at every device if you can do it. So if you can put the telephone in the circuit, if you can put the access switch in the whole thing here that's doing all this determination of which packets are going to be put in the high priority queue and which packets are going in the low priority queue, try to do that. Try to classify and mark traffic as close to the source as possible. Of course, we want the Cisco over IP telephone to be a trusted port, and for him to put up precedence values and classification values so that his traffic will, from the very get-go, be given the best quality handling. And try to shape and police traffic as close to their sources as possible. Okay, that's the last one here. Please try to view these videos. The guy there is kind of funny, but he also has a good explanation of some of these things here. I just have not possible technically for me to broadcast these videos to you. I've got to call into the help desk for the Blackboard to see if this is possible to do it, but I haven't been able to get it to work. Okay, guys, so that's all we're going to cover today. There were no labs assigned for this week, and next week we'll continue on with more chapters. So thank you very much for attending today, and I look forward to seeing all you guys next time. And this is Mark muting and signing off.